Hi. Now in today's video lecture, we will go through valence shell electron pair theory, right? VSEPR theory. And basically what this theory tells us, it tells us the shapes of covalent molecules, right? Before this video lecture, we have gone through Levi's and Langmuir theory of covalent molecules, right? Where Levi's theory helps us understand how covalent bond formation takes place, right? Using sharing of electrons, right? How covalent bond formation takes place via sharing of electrons. This was explained by Levi's theory, right? But Levi's theory never told us anything about the shapes of molecules, right? Now the shapes of molecules would be explained by VSEPR theory, right? Valence shell electron pair repulsion theory. If you just look at the word, if you just look at the full form of this theory, it's VSEPR, right? It has valence shell, it has electron pair, it has repulsion, right? All these terms, if you understand, you will understand this theory, right? It's simple. So the first important point regarding this theory is that this theory was proposed by Sidgwick and Powell, and later it was improved by Nihlholm and Gillespie, right? What improvement did they give? That's important to understand, right? This was proposed by Sidgwick and Powell, right? And later improved by Gillespie and Nihlholm, right? Now electron pair, this is important in VSEPR theory, right? And repulsion term, right? How electron pair, repulsion and valence shell, right? These are related, we'll see. In the previous video lecture, when we understood the concept of covalent bonding, how covalent bond formation takes place, we understood that there were two types of electron pair. One that took part in bonding, that was bonding pair of electrons, we also call it as shared pair of electrons, and the other one is your non-bonding pair of electrons, that was also called as lone pair of electrons, right? So we have two types of electron pairs, lone pair of electrons and bond pair of electrons, right? And these electron pairs, right, these electron pairs are surrounding the central metal atom, the central atom, right, in covalent molecules, right? So these surround the central atom in covalent molecules, right? So the valence shell, right, of central metal atom has electron pairs which are lone pairs and bond pairs, right? So valence shell stands for the valence shell of the metal atom that has lone pair and bond pairs, right? Now what does this term repulsion means? What does this term repulsion means? Here repulsion stands for repulsion between lone pair and bond pairs, right? Or repulsion between lone pair, bond pair, lone pair and lone pair, depending on the number of lone pair and bond pairs that central metal atom has, right? It's the repulsion, right? So repulsion stands for repulsion between lone pair or bond pair, or lone pair, bond pair. We'll understand more, we'll just look more on this, right? So if you understand these things, it would be easy for you, right? So the shape of the molecule is, right, what actually the shape of the molecule or what shape the molecule will take depends on your lone pair and bond pair, right, and the repulsion between them, right? So the shape, that's why we say that the VSEPR theory will tell us the shape of the molecules, right? And this is how it will tell us that VSEPR, it tells us the shape of molecules is based on electron pairs, which are lone pair and bond pair, right, and repulsion between them. Right, why repulsion between because these lone pairs and bond pairs consist of electrons. These are nothing but electron clouds, right? So if they are close to one another, they will repel one another, right? They will try to force one another to go as far apart as possible from one another. They want to be at maximum distance from one another, right? This has important thing to play, that they are at maximum distance from one another. We'll just understand that in a moment, right? So here we know two things most important, that shape of the molecule is decided by the electron pairs, lone pair and bond pairs, and the repulsion between the lone pair and bond pairs. The final shape of the molecule would be decided by the repulsion between these lone pairs and bond pair of electrons, right? Now let's just quickly understand one covalent molecule, right, based on the bonding in covalent molecule based on the Levi's concept, right, so that we are again clear with the concept of lone pair and bond pair, right? If this is your, let's look at over here, let me draw here, right, if this is your nitrogen, where we are taking the example of ammonia molecule, right? Ammonia has, we know it has 5 electrons in its outermost shell, right? This is hydrogen, right? Hydrogen has 1 electron in its outermost shell. Hydrogen will try to acquire 2 electrons. Each of the hydrogen atoms will try to acquire 2 electrons in the outermost shell, whereas nitrogen will try to acquire 8 electrons in the outermost shell, right? It's like this. So each of the hydrogen atom will share 1 electron from nitrogen atom, right? Now, since sharing is taking place between electrons on hydrogen, right, and electron on nitrogen, right, what it is forming a pair of electrons. This would be called as shared pair of electrons, because this pair of electron has resulted as a result of sharing between nitrogen and hydrogen, sharing of electrons between nitrogen and hydrogen. So this is your shared pair of electrons, right? And it is due to this shared pair of electrons that a bond will get formed between nitrogen and hydrogen, right? So bond will get formed due to this shared pair, right? Similarly, this is also a shared pair, this is again a shared pair. We have these 2 electrons which are not involved in any kind of sharing, right, in this molecule. So these 2 electrons are not involved in sharing or bonding with any of the atoms, right? So this is known as, this is your lone pair of electrons, right? This is your lone pair of electrons, which we also call it as non-bonding electron, non-bonding pair of electron, because this is not involved in bonding, right? Now one important thing about lone pair and shared pair is that this shared pair belong to both the atoms, while this lone pair belong to the central atom only, right? So lone pair belong to central atom only, and bond pair belong to the 2 atoms, right? As a result of which this shared pair of electron has been formed, right? So this is the concept of lone pair and bond pair, right? Now since these lone pair and bond pairs are nothing but electrons, electron cloud, right? So if this is your nitrogen molecule, if you imagine this is your ammonia molecule, this is your lone shared pair, this is the shared pair, this is the shared pair, because one shared pair represents a bond which is represented by a dash, right? And this is your lone pair. These are electron clouds. Now this shared pair belong to these two atoms, nitrogen and hydrogen, and this belongs to only nitrogen, right? So here we have 3 bond pairs and 1 lone pair, right? Now since I said that these are nothing but electron clouds, right? So they will suffer a force of repulsion. There is a force of repulsion between bond pairs and lone pair and force of repulsion between lone pair and bond pair and lone pair bond pair. For example, this is the lone pair, right, and this is your bond pair. This is your bond pair. So here you can see we have only one lone pair, so there is a force of repulsion between this lone pair and this bond pair, this lone pair and this bond pair, force of repulsion. Similarly, we have force of repulsion between these two bond pair of electrons, right? So it is this force of repulsion, right, that will decide the shape of the molecules, right? Now I've just mentioned over here repulsion between lone pair, bond pair, lone pair, bond pair. This is what it means here. Now, right? Now, this is the central metal atom that we will call from now onwards. Central atom, not metal, since this is not a metal, it's a central atom. Right? Central metal atom, we generally use this term in coordination chemistry that we will do in future. Right? That's a different chapter of inorganic chemistry. Right? So now we are clear about the lone pair of electrons, the bond pair of electrons, right, and the repulsion between the lone pair and bond pair of electrons, right? And it is these repulsion between lone pair and bond pairs and the number of lone pair and bond pairs that will decide the shape of the molecules, right? So shape of the molecules will depend on number of bond pair of electrons and lone pair of electrons, right, and the repulsion between them, between these terms, right? So we'll look into what it means is when I say the number of bond pairs and lone pairs. Suppose I have one lone pair here, right? If I have say one more lone pair on nitrogen atom, then the shape of the molecule will change. Or if I don't have say any lone pair here in this molecule, then the shape of the molecule would be different. Why? Because of the different amount of repulsion between lone pair and bond pairs, right? Now the important thing is the repulsion between these lone pair and bond pairs, these 3 repulsions are not same, are not equal. These repulsions are different, right? The force of repulsion is different, right? So here the force of repulsion between lone pair is maximum. The repulsion between lone pair is maximum, and repulsion between bond pair is minimum, right? And between lone pair and bond pair is between these two, right? So force of repulsion is lone pair is maximum. After this, your lone pair and bond pair, then you have minimum repulsion between lone pair and bond pair. This is important, right? Now, what is the reason that the force of repulsion is maximum between lone pair, right, and minimum between, this is your bond pair, I'm sorry, minimum between bond pair. This is what was improvement that I was talking about in the beginning. This improvement was given by Nyholm and Gillespie, right? However you pronounce the name of the scientist, I said Gillespie, right? So what they said, what Gillespie and Nyholm observed, that the force of repulsion between these pairs, right? What they said is that this lone pair, right? This lone pair of electrons, this nitrogen has one lone pair, right? This lone pair of electron belong to central atom only, right? And this bond pair belong to both the atoms. It belongs to both the atoms, right? Since this lone pair, right, this lone pair is only on this central atom, right? So the size of this lone pair, or the space occupied by this lone pair, is maximum, right? The space occupied, since this lone pair, right, is localized on this one atom only, right? So the space that would be occupied by this lone pair would be more, right, compared to these bond pairs, because these bond pairs belong to nitrogen and hydrogen, right? So the space that would be occupied by bond pair would be less compared to lone pair. Lone pair, the electron cloud of lone pair will occupy more space, right, because it's localized on one atom only, right? So this is the improvement, right? So that is why they said that since the electron cloud of lone pair is bigger, right, compared to bond pair, so the force of repulsion between lone pair is maximum, right? That is why the force of repulsion is maximum in case of lone pair, right? So this belongs to central atom only, this lone pair, right? So the space occupied by lone pair would be more compared to bond pair, right? Since this space occupied by lone pair is more, right? So if you have, say, two lone pairs, then the force of repulsion between the lone pairs would be maximum, right? Because the bigger they are, right, if they are bigger, then they are more close to one another. If they are more close to one another, the force of repulsion would be maximum, right? So that is why the force of repulsion is maximum in case of lone pair because of their size, right, or the space occupied by the electron cloud of lone pairs, right? So that is why the force of repulsion is maximum. Now let's study more about this lone pair and bond pairs, because these are what will decide the shape of the molecules. These lone pair and bond pairs, since I said that they experience the force of repulsion, right, and we know that if there is any kind of repulsive force, right, then that will try to destabilize the molecule, right, or that will increase the energy. And we know that every system will try to acquire a state of minimum energy, right, and this force of repulsion will increase the energy, right? Since this force of repulsion is trying to increase the energy, so this molecule will try to arrange, or this lone pair and bond pairs would be arranged right around this central nitrogen atom in this case, such that the force of repulsion is minimum, right? Between these three force of repulsion should be minimum, right? So what these lone pair and bond pairs will do, due to the force of repulsion, right, they will try to be as away from one another as possible, right, so that the force of repulsion is minimum, and the energy is minimum and stability is maximum, right? So since these pair of electron pairs experience a force of repulsion, right, that will decrease the stability of the molecule, I'm sorry, right? So this force of repulsion will decrease the stability of the molecule. So in order to acquire maximum stability, right, or minimum energy, these lone pair and bond pairs will try to be as far apart as possible from one another. They will try to be as distant from one another, right, so that the force of repulsion is minimum and stability is maximum, right? This is important. So when they arrange themselves, right, far apart from one another, they will acquire definite positions, right? They will acquire definite positions. It is due to these definite positions occupied by lone pair and bond pair that these molecules have definite shapes and geometry, right? Because that's what we were trying to say in the beginning, that the shape of the molecules would be decided by the lone pair and bond pair and the repulsion between them, right? It is due to these repulsion between them that they will arrange, right, themselves, right, so as to have minimum repulsive force, right? So due to the repulsion between them, these electron pairs, which are bond pair and lone pairs, will arrange themselves as far apart from one another, so as to have minimum repulsion and maximum stability, right? Because more is the repulsion, that will increase the energy of the system, and increasing the energy of the molecule means it will destabilize the molecule, right? So when they will move away from one another in definite positions, that will decrease the force of repulsion between them, because they are similarly charged. If they are far apart from, the more close they are, the maximum repulsion they will face. If the more distant they are, the force of repulsion would be minimum or no force of repulsion, right? So in order to stabilize the molecule or to have state of minimum energy, these electron pairs will arrange themselves far apart from one another, so as to have minimum repulsive force between them, right? And in order to do so, they will acquire, or they will take definite positions around the central metal atom, right? And due to these definite positions, these molecules have definite shape and geometry, right? So these electron pairs, due to this repulsive force, will take definite positions, right, due to which these molecules have definite shape and geometry, right? This is the reason why every molecule has definite shape and geometry, right? Just remember one thing, that geometry or any shape of the molecule would be decided by the lone pair and bond pair surrounding the central metal atom, right? And it is the shape of molecules is based on electron pairs and repulsion between them, right? So since they are similarly charged, due to the repulsive force, electron pair will arrange themselves as far apart from one another, right? They will arrange themselves at maximum distances, so that they can have minimum or no repulsive force, right? So when they arrange themselves as far apart from one another, they will take definite positions, right? Fixed definite positions, due to which these covalent molecules will have definite geometry, right? Now this definite geometry, right, this definite geometry depend on, or the shape of the molecule will depend on the number of bond pairs and lone pairs, right? We will see how it depends on the number of lone pairs and bond pairs, right? Let's quickly see, let's quickly take one example, right? Let's take the example of, let's take one example where we have, first we say that the shape of the molecule depends on the electron pairs. Suppose we have 3 electron pairs, right? And out of these 3 electron pairs, we'll see the bond pair and lone pair. Say we have 3 bond pairs and 1 and 0 lone pairs, right? So in this case, the molecule will have, when there are no lone pairs, you just have bond pairs, it would be like this, right? 3 bond pairs, there are no lone pairs. You can see that these are 3 bonds. Molecule is of the type AB3, right? The shape that is taken by a molecule that has 3 bond pairs is your triangular planar, right? Example of this molecule is BF3, right? So the molecule, the shape is triangular planar, right? Shape is triangular planar, right? When we have 3 bond pairs, 0 lone pairs. Now we will see if we have same number of electron pairs, but instead of 3 bond pairs, we have 2 bond pairs and 1 lone pair, right? If we have, so the molecule would be of type, right? If what I do is, now the bond pair and lone pair, 2 bond pair and 1 lone pair, total electron pairs remain the same, right? 3, 1 is lone pair, 2 are bond pairs. Now the shape of the molecule would be, it would be like this. Molecule is of the type AB2, 2 bond pairs and 1 lone pair. AB2L means 2 bond pair, 1 lone pair. Here the molecule is AB3, 3 bond pairs, right? So shape of this molecule is your V-shaped. This is a V-shaped molecule, bent. We call it a bent shaped molecule, right? So you can see that how presence of 1 lone pair instead of bond pair changed the shape of the molecule from triangular to bent shaped, right? Now why it happened, you can see that this is your triangular planar, right? This has a triangular shape. Now if I have 1 lone pair here, if you look at this, if you look at the sequence, lone pair is maximum, then you have lone pair, then you have bond pair. So here the repulsion between the lone pair and bond pair has now increased. Here repulsion is between bond pair, right? Here repulsion is bond pair and bond pair, right? This repulsion is less. Here the repulsion is now lone pair and bond pair, right? This repulsion is more, right, compared to this. So this molecule will be like bent, right? Due to this repulsive force, these bond pairs and lone pairs will arrange themselves. They will try to be away from one another, right? Because electron cloud of this lone pair is bigger. So there is maximum repulsion, or there is more repulsion compared to this. So that is why presence of 1 lone pair has changed the shape of the molecule from triangular planar to V-shaped, right? Because of increased repulsive force, these bond pairs and lone pairs will move far apart from one another, thereby acquiring V-shaped or bent shaped, right? I hope this is clear. We'll just take some more examples in next video lecture. Thanks.